Enzymes! These tiny titans are essential to life as we know it. They are the catalysts that make the molecules of our cells dance. They are proteins, intricately folded into complex three-dimensional shapes. Their unique forms create special pockets. These pockets are called active sites. Active sites are where the magic happens. Each active site is specifically designed to bind to a particular molecule. This molecule is called a substrate. When a substrate nestles into an enzyme's active site, the enzyme helps the substrate transform. This transformation could involve breaking the substrate apart or combining it with another molecule. Enzymes work their wonders by lowering the activation energy of a reaction. Activation energy is like a hill that molecules need to climb to react. Enzymes smooth out this hill. They make it easier for reactions to occur. This ability to speed up reactions is what makes enzymes so crucial to life. Without enzymes, the chemical reactions in our cells would proceed far too slowly. We would cease to exist. Enzyme kinetics is the study of how fast these enzymatic reactions occur. It gives us a window into the inner workings of these molecular machines. It helps us understand the very processes that keep us alive. Imagine a factory with thousands of assembly lines. Each line is an enzyme, diligently working on its specific task. The rate at which these assembly lines churn out products is the reaction velocity. In the world of enzymes, reaction velocity tells us how many substrate molecules are transformed into products per unit of time. We can think of reaction velocity as the speed of the enzyme's dance. A fast dance means a high reaction velocity, while a slow dance indicates a lower one. Now, how do we measure this molecular tango? One way is to focus on the very beginning of the dance, the initial reaction velocity. At the start of a reaction, there's a surplus of substrate molecules eager to join the dance floor. The enzyme, like a tireless choreographer, quickly pairs up with these substrates. This initial period where the enzyme is saturated with substrate gives us a clear picture of how fast the enzyme can work. Measuring the initial reaction velocity helps us avoid complications. As the reaction progresses, the substrate concentration decreases. This can slow down the reaction rate. By focusing on the initial phase, we get a pure measure of the enzyme's catalytic power. In the grand equation of enzyme kinetics, two constants reign supreme, Vmax and Km. These constants are like an enzyme's vital statistics. They reveal an enzyme's personality and its catalytic prowess. Vmax represents the maximum velocity an enzyme can achieve. Imagine our enzyme is a race car. Vmax is its top speed, the limit beyond which it cannot go, no matter how much fuel you provide. Km, on the other hand, is a measure of an enzyme's affinity for its substrate. A low Km value indicates a strong attraction between the enzyme and its substrate, like a love story written in the language of molecules. The enzyme binds tightly to its substrate, even at low concentrations. A high Km suggests a weaker affinity, a casual acquaintance rather than a passionate embrace. The enzyme requires a higher concentration of substrate to reach its maximum catalytic potential. Together, Vmax and Km paint a complete picture of an enzyme's character. They tell us how fast an enzyme can work and how much it desires its substrate. These constants are essential for understanding the intricate dance of enzymes and their role in the symphony of life. Now, let's introduce some party crashers to our enzyme soiree. The inhibitors. These molecules can interfere with the enzyme's dance, either slowing it down or stopping it altogether. Imagine them as mischievous guests who disrupt the rhythm of the party. There are two main types of inhibitors, competitive and non-competitive. Competitive inhibitors, true to their name, compete with the substrate for the enzyme's attention. They try to outbid the substrate for a spot in the enzyme's active site. Non-competitive inhibitors, on the other hand, are sneakier. They bind to a different site on the enzyme, changing the enzyme's shape and disrupting its ability to interact with the substrate. It's like subtly sabotaging the dance floor itself. These inhibitors play crucial roles in regulating enzyme activity within cells. By controlling the pace of enzymatic reactions, they ensure that the complex machinery of life operates in harmony. Understanding enzyme kinetics and the role of inhibitors is key to unraveling the secrets of countless biological processes. From developing new drugs to understanding the causes of diseases, enzyme kinetics holds the key to unlocking a deeper understanding of life itself.